8.1 Day 2. We'll briefly talk about problem number 10 and we'll get its formula. Our discussion of convergence or divergence should help with 31 and 45. The squeeze theorem in this lesson is adapted to sequences, and we'll get a term called monotonic, and we will show that a pattern is strictly increasing or decreasing, which shows that it's monotonic. And finally, we'll have the monotonic sequence theorem along with a proof using recursion and induction. 45 and 55 should have been added to the homework list. If you don't have that already added, please do so. So let's go back to number 10. Number 10 simply alternates 5, 1, 5, 1, 5, 1. And the challenge is to be able to come up with a formula for that as an nth term formula. The secret is to think of the average of the two. So 5 plus 1 over 2, of course, is 3. And if we think of this as 3 plus 2, then this would be 3 minus 2. 3 plus 2, 3 minus 2. So sometimes we're adding 2, sometimes we're subtracting 2. So the nth term formula would be 3, and then an alternating in sign times 2. How do we want it to alternate? With n as the power, or n plus 1, or n minus 1? N plus 1 would work because if it's the first term, I put a 1 in here, I get negative 1 squared, which makes it positive, and I would add 2. When n is 2, I'd get negative 1 to the third, which would be negative, and of course subtracting 2, I'd get 1, and so on. With regard to convergence or divergence, of course the pattern diverges. It continues to alternate between two values and does not head towards a single number, and therefore the pattern or the nth term diverges. And something similar will happen on number 31. We'll briefly talk about the squeeze theorem. You may read it in the lesson. To save time, I'm not going to rewrite it. But it's the same as we've used in the past. If we're not sure of what a particular pattern is doing, we may compare it to one that's similar. So I'm going to do number 19 for you, at least help you see how to start it. The nth term formula for number 19 is an alternating in sign, negative 1 to the n minus 1, times n, and that's all divided by n squared plus 1. If we think about reducing it, it is the comparison. Out near infinity, the negative 1 doesn't do much. N over n squared is similar to 1 over n. So that's going to be our comparison. We want to compare to 1 over n. Of course, we're going to also have to apply theorem 4, which says, let's see what happens with the absolute value, and if it would head towards 0, then the nth term with the alternating in sign would head towards 0. So it's true we would take the absolute value of this. So the alternating would drop out, and the absolute value version would be n over n squared plus 1. And if we divide everything by n, we'd get 1 over n plus 1 over n. Now how does that compare to 1 over n itself? Well, we could see that there's more in the denominator. So we've established an inequality that, of course, n is an integer. For n bigger than or equal to 1, this fraction is smaller than that one. The second component is to declare what this one is doing. Of course, this is all bigger than 0, so that's what it's going to get squeezed between 0 and 1 over n. We do know what this one does. The limit of 1 over n as n goes toward infinity is also 0. So the one in the middle must go to 0. So the limit of the absolute value of a sub n is also 0. And by theorem 4, the version without the absolute value must do the same and head towards 0. So the squeeze theorem is much the same as it had been in the past. You would compare with a simplified form of the nth term and then declare what it does. And the one in the middle, which is the one you were given, must do the same. Continuing, we have a term referred to as monotonic. And if a pattern is monotonic, it means the sequence is either strictly increasing or strictly decreasing. What you can do is compare the nth term with the nth plus 1 term. If it's true that the nth plus 1 term is smaller, of course it must be decreasing. If we're given 3 over n plus 5 is the nth term formula for a particular sequence, the way we get the nth plus 1 term is to replace n with n plus 1. Certainly there is more in the denominator here, which makes the fraction smaller. And it is true that the nth term is bigger than the nth plus 1 term, and this would be true for all n bigger than or equal to 1, and therefore we've shown that it would be decreasing. It does mean it's monotonic, it's doing one thing only, in this case decreasing. A second example would be n over n squared plus 1. And it's not so obvious this time when you replace n with n plus 1. If we go ahead and do that, they tell us that we're to show it's decreasing, so it ought to. But if you replace n with n plus 1, you get n plus 1 over n plus 1 squared plus 1. And when we compare that to the nth term, it's not real obvious that this guy is smaller and it is decreasing. So what we do is we carry out the algebra of simplifying and arrive at some algebraic truth, which means the previous steps must also be true. So if we cross multiply n plus 1 times n squared plus 1, n times the n plus 1 squared plus 1, and skipping some of the details of all the algebra, this left side becomes n cubed plus n squared plus n plus 1. The right side becomes n cubed plus 2n squared plus 2n. If we subtract n cubed, they'll cancel. If we subtract n squared, we'll get an n squared on the right. And if we subtract n, we'll get an n on the right. And we'll only have a 1 left on the left side. And since n is greater than or equal to 1, it is true that this has to be true. 1 is smaller than n squared plus 1. I'm sorry, n squared plus n. And since this must be true, it means that all the steps previously have to be true. So it's true that it is decreasing because the nth plus 1 term has to be smaller than the nth term. Another approach, not shown in the lesson, but certainly would be acceptable, would be to take the derivative of the nth term. So if you have an nth term formula and you take its derivative, of course if it's greater than 0, it must be increasing. And if the nth term formula, its derivative would be negative, it must be decreasing. Sometimes that comes in handy in homework to, again, make it a little bit quicker. Continuing on,